Today, I'm going to introduce my PhD work, Systematic Modeling and Design of Sparse Tensor Accelerators. Throughout this talk, we're going to focus on what we call sparse tensor algebra, which refers to tensor algebra computations that involve zero values. So for example, in this figure, we're showing a sparse matrix multiplication example with two sparse matrices, A and B. And sparse tensor algebra is widely used in many popular applications, including deep neural networks, circuit simulations, and graph analytics. All of these popular applications share the same common characteristics of being data and computation intensive. As a result, processing them on general purpose processors often introduce inefficient processing, such as high energy consumption and processing latency. So to solve this problem, hardware designers have been focusing on developing various domain-specific accelerators. In this case, a lot of designers are motivated by the sparsity in the sparse tensor algebra workloads. So sparsity can introduce many potential opportunities for hardware savings. For example, we can compress away the zero values in our tensors, meaning that we can only store the non-zero values in the hardware, and this reduces the hardware capacity requirement for our accelerator design. In addition, sparsity also introduces what we call ineffectual computations, such as multiplications and additions involving zero values. And these ineffectual computations can also be eliminated to further improve the hardware processing efficiency. And we call hardware designs that focus on recognizing the zeros and accelerate sparse tensor algebra, sparse tensor accelerators. And because of the popularity of this kernel, it is very important as computer architects or hardware designers to develop next generation sparse tensor accelerators so that we can always translate such opportunities into hardware savings. So the goal of this thesis is first to identify what are the challenges for developing these next generation sparse tensor accelerators, and with the challenge identified, can we propose some solutions to the different challenges? And now the question we probably want to ask is, okay, so what is the ultimate challenge that we're going to face if we want to design such a design? As computer architects, we always want to propose designs that can accelerate as many workloads as possible. So in the world of sparse tensor algebra, different workloads often introduce different sparsity characteristics, which, for example, can be the global degree of sparsity in the tensors. So the first challenge that we're facing is really to develop efficient and flexible hardware so that we can always accelerate workloads with different sparsity characteristics. However, before we really go ahead and propose such a design, we want to learn from existing works. So we are facing an even more fundamental challenge of having a quick and systematic way to have a qualitative understanding of the existing work's insights. And furthermore, we want to take a step further and perform quantitative analysis to compare the designs that we're interested in, as well as explore the designs that we have in the potential design space. So this work aims to solve the challenges with several solutions. First, we propose a systematic understanding of the design space of sparse tensor accelerators by a set of well-defined sparse acceleration features, which I'll cover later. And with a good understanding of the design space, we propose a Sparseloop modeling infrastructure, which is an early design stage modeling infrastructure that allows designers to evaluate and explore the designs they have in mind. Employing Sparseloop, we can then go ahead and propose different accelerator designs. And our goal is to have them being simultaneously efficient and flexible. So these are the high-level solutions. And while we were studying these solutions, we find many interesting research questions. And here we show a list of contributions of our work. Of course, I'm not going to talk about each item, and you'll see all of the major contributions later. And specifically for this talk, we're going to focus on the most important ones. However, we do have some additional publications that either cover the modeling methodologies or the accelerator designs. So if you're interested in learning more beyond what I'm going to cover today, please definitely check out the publications. With a high-level understanding of the challenges and solutions, let's first take a deeper dive into the first contribution. As I have said, in order to really propose a good accelerator design, we want to understand the existing design space. So what does the existing sparse tensor accelerator design space look like? Because of the promising opportunities introduced by sparse tensor algebra, there actually exist ample sparse tensor accelerators. Here in these figures, we're showing some example designs. As you can see, different accelerators can propose different architectural organizations, and most importantly, they can propose sparsity-related hardware optimizations that are different from each other. However, we make the observation that all of these insights are proposed with design-specific terminologies that are only developed by the authors of these works. So it makes it really challenging for general hardware designers to have a good understanding or a quick understanding of the insights that's proposed by these designs. So this phenomenon makes it the sparse tensor accelerator design space not only very large, but also very unstructured and confusing. So to solve the problem, we make the observation that all of these proposed sparsity-related optimizations can be classified into 3 high-level hardware acceleration features, which I'll refer to as AFs. The first one is called a format. Format refers to the choice of tensor representations when we want to store them in the hardware. Of course, the easiest way to do this is let's just store the tensors as they are in the storage units. So here we're showing an example vector, and we refer to this way of storing these tensors as uncompressed representation. But as I have already alluded to, we can actually compress away the zero values. So if we look at a compressed tensor, you might have noticed that as a hardware, it is really hard to then figure out where each non-zero value sits in the original uncompressed vector. In specific, we refer to the locations of these non-zero values, the coordinates. So these hardware accelerator designers then propose different compressed formats which capture the location of each non-zero value with additional metadata. The metadata is responsible for telling the hardware where each non-zero value sits. And specifically in this example, we're directly carrying the coordinate for each non-zero value. And we refer to this format as coordinate payload representation. As you can imagine, different designs can propose different ways of carrying metadata. So for example, bitmask and run length encoding are 2 other ways that also carry different kinds of metadata for hardware to identify the non-zero value locations. In general, having a special representation format can help us to reduce the required hardware capacity and can also help us to reduce the energy consumption because we don't need to access the zero values anymore in our storage. The second sparse acceleration feature is called gating, which is related to the fact that we can eliminate ineffectual operations by keeping the hardware unit staying idle. So let's take a more concrete example to see what we mean and what's the impact of gating. In this example, we're going to use a dot product of vectors A and B. And in a dot product, what we usually do is just multiply the corresponding entries in the vectors and accumulate them to form the output. So what are the hardware operations at a high level that are associated with this processing? If we don't consider any optimizations, what we want to do is we'll fetch the operand with memory accesses, and with the operand fetch, we'll do the computation. And in this simple example, for each time step, we're going to fetch the corresponding pair of operands to perform the computation. So as you can see, in order to do this processing, it takes 6 steps. You probably have already noticed that we are already introducing many ineffectual computations with this simple example. In fact, it's 50% of our computations. So to solve this problem, this is where gating comes into the picture. If we apply gating to the computation units, the computation unit will stay idle whenever it realizes there's a zero value in the operand. So as a result, as you can see, some of the computations become a gate, which is the icon that I'll use to represent gating. And we can further apply gating to the memory accesses. For example, gate the operand read of B. And in this case, we're getting rid of even more hardware operations. And of course, if we imagine we have some zero values in operand B as well, then the gating of compute will take effect. So this is at a high level how gating can come into the picture and how it can help us to save hardware operations. In general, gating helps us to save energy, and you probably have noticed we still take 6 steps to finish the processing. So that naturally leads to the next sparse acceleration feature, which is called skipping. Skipping is similar to gating that it also eliminates hardware operations associated with ineffectual computations. However, instead of only letting the hardware stay idle, it also directly fast forward to the next effectual computation. So let's take a look at one example using our previous workload of skipping. In this example, we're applying skipping to all of the memory accesses and compute. And as you can see here, we directly fast forward to the first effectual computation with C and I and perform the computation. So now our processing only takes 3 time steps, which is additional savings on latency. Okay, so we have covered the 3 high-level sparse acceleration features. I'm going to refer to them as SAFs, and please definitely keep in mind that whenever I see SAF, I mean these icons here. And now we're equipped with some terminology to describe existing designs. We have been very abstract about the processing, the memory accesses, but in order to really define an accelerator or describe an accelerator, we need to consider its architectural organization. And in this example, we are going to use a simple architectural organization with 2 levels of memory, global buffer, and set of parallel computation units. We propose to describe the sparsity-related hardware optimizations by applying the SAFs to different levels in the architecture. And because the SAFs can be applied to different tensors in our workload, we're going to use different color coding for our icons to showcase that. So what does all that mean? Let's use one example to show how we can do this. Here, we want to describe the sparsity-related optimizations proposed by the Aries architecture. Aries is a very famous DNN accelerator, and it has some lightweight optimization towards sparsity. More specifically, it applies a special representation format in the innermost storage level, and it also applies gating to the different operands and computes. So Aries only saves energy, as you can see here. The second generation of Aries improves the optimization they do to sparsity. So as shown in this figure, we now apply special representation format to multiple levels in our architecture's storage units, and we now perform skipping instead of gating for our innermost level and compute units. Another example would be the extensor architecture, which is focuses on accelerating the more sparser workloads, and specifically it performs hierarchical skipping in their architecture. So as you can see, for both memory levels, we're introducing skipping for all of the operands. So this makes it to have the ability to give very high speed up if the workload is very sparse. So at a high level, we are able to enable a clear qualitative description of existing designs by using the SAFs and assigning them to different levels in the architecture. Okay, so before we can go ahead, we need to do more analysis. So we need a quantitative analysis of the designs that we're interested in. And for early design stage exploration, what do we need in terms of requirement for this modeling framework? First, we want it to be fast because we will be evaluating a lot of different designs in the design space. So we want short turnaround time. We want to be accurate so that we can have enough trust in the modeling result that we produce. Finally, we want it to be flexible so that diverse designs can be modeled in the design space. So the question now is, do we have any way to find an existing work that meets all of the requirements? Unfortunately, we find existing modeling frameworks insufficient for our goals. The first example class of existing works is called cycle-level simulators or design-specific simulators. They focus on modeling the details of the architecture. So as a result, they are often slow because too much of the information needs to be captured, and they're often not parameterized enough to support the diverse designs in the design space, so not flexible enough. Another class of modeling framework is called general analytical modeling frameworks. These frameworks uses mathematical derivations to derive the activities of the high-level or important components in our architecture. As a result, they are very flexible and fast. However, we didn't find any existing analytical modeling framework provides support for sparsity analysis. So this can make them inaccurate if we are interested in architectures that exploit sparsity. So all of these limitations motivate our second major contribution of this thesis, which is the proposal of a modeling framework called Sparseloop. The goal of Sparseloop is to enable early design stage modeling of the different accelerator designs we have in mind. Before I dive into the details of this modeling framework, let's first take a look at a high level. How does this infrastructure look like? The first input into Sparseloop is called workload. Workload can be, for example, a layer in a convolutional neural networks. And what workload specifies is first the algorithm. Is it a convolution or matrix multiplication? And the shape of the tensors. For example, is it a 4x4 tensor or 8x8 tensor? And since we're looking at sparse tensor algebra, it needs to carry information about the sparsity of the tensors. The next input into Sparseloop is called the architecture specification, which includes both the architecture organization and the sparse acceleration features applied to different levels in the architecture. So this is the description that we have shown so many times in the previous section. The next input is the mapping, which at a high level defines how can I schedule my workload onto the architecture. And I'm going to show example mapping processing flows in the next slides. So what Sparseloop does is it analyzes the three inputs, generate the runtime activity of the components in the architecture, and in order to take hardware details into account, it communicates with an energy and area estimation backend called Accele, and in the end, it's able to generate the cycle counts, the energy consumption, and the area consumption of the specific evaluation that we want to run. So now we have a good understanding of the framework. What are some challenges that we're facing when we are developing the framework? The first very important challenge that we have realized is there are a lot of complex interactions between the inputs to Sparseloop modeling infrastructure because each input has a lot of information specified. So if we just naively model all of the interactions simultaneously, it can lead to very high modeling complexity, which then will lead to slow modeling speed. And that's not desirable at all for an early design stage modeling framework. So to solve that problem, Sparseloop proposes a progressive modeling procedure. So as you can see here, internally in the infrastructure, we have three modeling steps: data flow modeling, SAF modeling, and microarchitecture modeling. Each of the steps focuses on a subset of the inputs or focuses on analyzing a subset of the interactions between the inputs. And by doing this, we're able to decouple the analysis and keep the modeling complexity tractable. So in the next set of slides, I'm going to at a high level talk about how each modeling step works. The first step is data flow modeling. Data flow modeling is a step that doesn't yet consider sparsity yet. So for the inputs, we don't consider the sparsity characterization of the workload tensors, and we don't consider the SAFs applied to the architecture. So what's the goal of this flow modeling? At a high level, the step aims to produce the uncompressed data movement between the memory levels and compute units, as well as the dense computation happening in the parallel computation units. And in order to understand how the data is transferred and compute has happened in parallel, let's use one example processing of an example tensor algebra workload with three tensors, A, B, and Z. Let's assume that they are small enough to fit in our global buffer in this architecture. What usually a sparse or a tensor accelerator does is to exploit the memory hierarchy by partitioning the workload tensors into smaller sub-tensors, which we refer to as a tile. And the tiles will be transferred to the inner level memories with smaller capacity, of course, for reuse. So one example would be we transfer different tiles in the first row of tensor A to the inner level buffers. As you can imagine, we can do this for all of the tensors in our workload, and we want to keep the smaller piece of data in the buffer as long as possible so that we can reduce the access cost to our global buffer. We can further split the tiles inside the buffer so that we can produce the operands for the parallel computation and then really do the computation in parallel to speed up our processing. Of course, the output of the compute will be sent and propagate all the way back to global buffer. So this will be one example way of scheduling the data movement. And of course, across time, different tiles will be sent to the different levels in the memory hierarchy, and they will be computed sequentially or in parallel. So this kind of scheduling is what the mapping input specification tells us. And by changing the mapping, we can have different ways of scheduling such data transfers and parallel compute. The goal of data flow modeling is to really analyze what are the traffic between the different memory levels and compute units. And you probably have already noticed that all of these tiles at this step are identical inside the memory storage units. So data flow modeling can actually perform very quick analysis by performing steady state modeling of all of these identical files without going through every single one of them. And as a result, we're able to quickly produce what we call the dense traffic, which includes both the memory movement and computation. So with the dense traffic produced, we want to now consider the sparsity information in our workload and architecture. So the goal of the second step, SEF modeling, is really to consider what are the impact of the SEF applied to the architecture on the dense traffic. And in order to do that, again, let's look at an example. So you probably have noticed that in this new setup, our tensors now consider sparsity. And these sparse tensors are also tiled in a similar fashion as we have just shown for the dense tensors. And in order to see some difference in terms of processing efficiency, we need to apply some SEFs into the architecture levels. And specifically, if you recall, this is the example of extensor style optimization with hierarchical skipping. So the question we want to ask is, by applying these SEFs, what is the impact? In order to analyze the impact, we really need to now look at the tiles transferred across time. As you can see here, for different time steps, we're transferring different tiles, and the traffic between the memory level and specifically on compute unit in this example will be impacted by the sparsity of each tile at different time steps. And you probably have noticed that these tiles are very different in terms of their sparsity characteristics, and specifically in this example, they have different degree of sparsity across time. So how can we take the different tiles into account when we analyze the impact on the traffic? Of course, the most naive solution to do this is, let's just traverse the exact data in all of the tiles that we're going to process, and let's analyze the per tile impact and aggregate it to a global impact. However, because our workloads are often very large with many large tensors, doing this can lead to very slow modeling speed, and that's, again, is very undesirable for us. So Sparseloop comes up with a solution which employs statistical tile sparsity characterizations to solve the problem. As you can see here, instead of looking every single tile at different time steps, we generate a tile sparsity probability distribution. What this distribution is telling us is that for a specific percentage of time, we're going to get a tile of a specific sparsity degree. And this allows us to not really look at the exact tiles and just use mathematical derivations to analyze what will be the impact globally. And recall that we don't really have this information in the input specification. So the responsibility of Sparseloop is to generate or derive the sparsity distribution based on the provided tensor sparsity characteristics that user will send into this infrastructure. And as you can imagine, different workload tensor sparsity characteristics will greatly impact the distribution of tile sparsity. So Sparseloop does support this analysis with different workload tensor sparsity models. For example, we provide a fixed structured sparsity model where the non-zero values in these tensors are well constrained so that all of the tiles will share the same sparsity. We could also have a uniform random model where the non-zero values are arbitrarily distributed in our tensor. In the specific case, the smaller tiles will have larger sparsity deviation and the larger tiles will have smaller sparsity deviation. And this could be an example density model that's widely used for unstructured prone DNNs where the weights can be removed randomly. We also provide what we call the banded distribution, which characterizes tensors with a dense diagonal. And this kind of density models could be popular for scientific simulations, such as circuit simulations or power simulations. So by allowing us to model the workload tensor and tile tensors sparsity characteristics in the statistical fashion, Sparseloop is able to maintain or ensure both the speed and accuracy of our modeling. And more specifically, in our internal implementation, we have a statistical sparsity characterization module that serves as the basis for two independent SEF analysis modules, gating skipping analysis and format analysis. We separate the SEF analysis to further reduce the complexity of our modeling. Yeah, so then the format analysis module is responsible for generating the metadata overhead as well as the required buffer capacity, because if we do compression, then a lot of the zero values will be removed for this memory level. In the end, this is actually all of the a lot of the complexity also comes into the picture. Well, we are applying these kind of impact to the dense overall traffic to finally generate the sparse traffic with what we call the scaling module. So with these kind of analysis, we derive the output of the second step with what we called a SEF modeling, and now we are ready with the sparse traffic. So the next step of this modeling flow is the microarchitecture modeling. This step considers more of the hardware details, and specifically, as I have quickly alluded to, this step interacts with the accelerate energy and area estimation backend, and it considers the implementation internally inside the memory levels. And specifically, for example, what are the controls in your memory levels and what is the exact implementation of your SRAMs. And it also considers similarly for the compute levels where what arithmetic computation actually happens in these hardware are all considered. So in the end, with these detailed information about the hardware, we can then generate the cycle counts. Yes. Yeah, so for example, one detail for the SRAM blocks would be what is the aspect ratio of your SRAM, how many banks. So all of this information will be specified, and because it impacts the overall, the cost of your SRAM accesses, it will all be considered by the backend as well as Sparseloop. Okay, so yeah, so we now have a high-level understanding of the modeling infrastructure. Let's take a look at some experimental results that we have generated to showcase how good that framework is. So first, we want to make sure that our simulation speed is still reasonable, and specifically the evaluation metric that we use for evaluating the speed is what we call compute simulated per host cycle, CPHC. And by host, we mean the machine that runs our modeling framework, so such as a CPU. And this is very similar to the millions instructions simulated per second metric that we use for general purpose simulatory evaluation. And at a high level, we want the CPHC to be higher so that we can have better simulation speed. And just as a reference point, we have less than 0.5 CPHC for normal cycle level simulators. For Sparseloop, we are able to achieve more than 1,000 CPHC for the workloads and accelerators that we have evaluated. This is due to the fact that we don't really traverse the exact workloads and we don't simulate a lot of the hardware details. Yes. Analyzing, modeling. Yes, fast modeling speed, new title. And so for example, if usually if you simulate the workload, it will take hours. Now, if with analytical modeling, you'll achieve less than second or seconds speed. And across, as I've said, we have validated this across various DNN accelerators, and it's always 2000x faster if we just perform analytical modeling than cycle level simulation. The next thing that we want to validate is the accuracy of the model. So we'll show an example architecture validation. This is a DSTC accelerator. The y-axis is showing the cycle counts, and the x-axis is showing the different workloads with different tensor sparsity or density. And the blue bars are the reference results, and the red bars are what's generated by the Sparseloop infrastructure. So as you can see here, for these validated workloads, we're able to maintain the absolute values of these cycle counts, and we are also able to maintain the relative trends, which is quite important for early design stage evaluation, because we do want to know how comparatively they perform, even if we don't have a lot of implementation details. In general, we have evaluated Sparseloop or validated Sparseloop across different sparse DNN accelerators and workloads. We are able to maintain less than 8% average error in cycle counts and energy consumption. So now that we have shown the framework is fast and accurate, we want to also show the flexibility of the framework. And because of time constraint, I'm going to show a simple example that can at a high level illustrate the idea. But in our papers, there are more in-depth studies. So specifically in this example, on the y-axis, we're showing the total energy consumption of a different hardware evaluating different workloads. On the x-axis, we're showing the various combinations of different SAFs applied to the same architecture organization. So basically, each combination will mean a different accelerator design. And the different colors are showing different components in the architecture, so global buffer or DRAM or computation units. We also evaluate different workloads as well, and specific in this case, there are different DNN layers. As you can see, Sparseloop is able to produce quick results and comparisons to give us some interesting overhead and savings analysis. For example, it shows that we are able to achieve 2x overall energy difference by applying more and more SAFs. It also tells us that when applying SAFs to different places in our hardware, we can introduce savings at different components. And of course, we would see different energy breakdown across the components or savings across components when we're running different workloads. So in general, we have been using Sparseloop to demonstrate the flexibility, and we are able to quickly identify the savings and overhead for different implementations of our hardware at early design space. So now that concludes the first part, which is a taxonomy and Sparseloop section. I would like to give a quick summary of my this class of works. First, we propose a systematic way to describe the design space. There are 3 sparse acceleration features, and we propose to apply them to each level in the memory in the architecture organization to describe different sparsity-related optimizations proposed by existing designs. We also, based on the understanding of the design space, propose the Sparseloop modeling infrastructure that performs progressive modeling with tractable complexity. We allow statistical modeling to balance accuracy and speed. And in the end, we're able to ensure both accuracy, speed, and flexibility. With our experiments, we have shown we achieve more than 2000x faster compared to cycle level simulations and accurate modeling as well as flexibility. So I will move on to a different topic. So any questions at this point for Sparseloop and design space? Okay, nice. Okay, no questions, right? Okay. So next I'm going to, because we now have understanding of the design space and Sparseloop modeling infrastructure, I'm going to introduce a DNN accelerator that we propose that's simultaneously efficient and flexible. We know that DNNs are very popular for many applications, and in order to make them work even better, different optimizations are applied to these models. And these models can introduce different sparsity. For example, in order to reduce the model size, pruning techniques are proposed to clip weights to 0 so that we can introduce sparse weight tensors. In addition, if we employ depth-wise separate layers, we also reduce the model size, but we didn't change the density of the weights. As you can imagine, the sparsity and density of activation tensors can also change depending on what optimization we apply to these DNN models. So in general, modern DNNs can have weights and activations that are either dense or sparse with various sparsity degrees. And by sparsity degrees, we mean the percentage of sparsity in our workload. So given the property of these modern DNNs, what are some ideal requirements for us in order to develop a sparsity in an accelerator? The first requirement is we want a flexible design. And I'm going to use this sparsity degree spectrum to illustrate the flexibility. On the left is 0% sparse, and on the right is 100% sparse. So for a flexible DNN design, we want it to cover a wide range of sparsity. So it should be able to translate a wide range of sparsity into hardware savings. And in addition, we want to cover many sparsity degrees within the wide range. In addition to flexibility, we also want the DNN accelerator to be efficient, meaning that we want to have low SAF implementation overhead for the way that we want to accelerate the workloads. And so an ideal DNN accelerator needs to be flexible and efficient. So again, the question I want to ask is there any existing work that meet our requirements? One popular class of existing work is called unstructured sparse accelerators, which is able to accelerate DNNs with arbitrarily distributed non-zero values. And as a result, if we look at the related sparsity spectrum, it is very flexible because it can continuously translate sparsity into savings. However, because it needs to support these complex workloads, it has to have a lot of hardware control. So workload balancing would be one example. And they also often have costly data flow to support such workload balancing. So they are often very inefficient as hardware accelerators. On the other hand, we can do structured sparse accelerator design where it focuses on accelerating DNNs with spatially constrained non-zero values. Here we use the famous NVIDIA Sparse Tensor Core as an example. As you can see here, it exploits per row 2 to 4 structure sparsity, where each row of 4 values have 2 of them being non-zero. And in this case, because the sparsity is so constrained, the design only requires little hardware overhead, so it is very efficient. However, if we look at the associated sparsity spectrum, it only supports 2 degrees, 0% and 50% sparse. So as a result, they are not flexible enough for us to use. And we might argue that we can easily improve the flexibility of the sparse tensor core design by just supporting more ratios. And here we refer to the sparsity pattern G to H. So using a 2 to 4, it will be G equal 2, H equal 4. So if we want to increase the flexibility, all we need to do is let's do more G to H ratios. For example, we could support 2 to 6 and 2 to 8, and this will add 2 more points in our spectrum. However, even if with a few sparsity degrees, this solution looks promising, it is not really scalable because the hardware complexity will increase approximately in proportion to the number of sparsity degrees that we want to support in this setup. So to solve this problem, we propose an efficient and flexible way to perform DNN acceleration with a novel sparsity pattern called hierarchical structure sparsity. So what is hierarchical structure sparsity? Hierarchical structure sparsity, or HSS, refers to the fact that we can compose G to H sparsity patterns in a hierarchical fashion, where each level in a hierarchy is referred to as a rank. So an n-rank HSS refers to the fact that we will have n G to H ratios, with each ratio being different in each rank. So that's still a little bit abstract. Let's use a concrete example to illustrate what does this pattern look like. So we have a dense vector. How can we introduce a 3 to 4, 2 to 4 HSS pattern? So this is a 2-rank HSS pattern. So we'll first introduce rank 1, 3 to 4. This refers to 3 non-empty blocks out of 4 blocks, where non-empty means dense. And blocks refers to, in this example, 4 values, which is a coarser granularity sparsity. And in this specific example, we have block 0, block 1, and block 3 being non-empty, and block 2 being empty. With rank 1 applied, we can further apply rank 0, which has a ratio of 2 to 4. And we apply this ratio to only the dense blocks. And in this case, block 0, 1, and 3 will have a 2 to 4 ratio. So this completes a very simple example of HSS pattern. And now, what are some benefits that this pattern can bring us? First, HSS introduces a more flexible way for us to express sparsity degrees. And in order to illustrate the idea, I'm going to use a 2-rank HSS. Rank 1 allows 4 different sparsity degrees, 4 to 4, 4 to 5, 4 to 6, and 4 to 7. And rank 0 allows 3 different sparsity degrees, 4 to 4, 2 to 4, and 1 to 4. As we have shown before, to construct HSS, we basically pick one ratio from each rank. So for example, we can pick a 4 to 5, 2 to 4 to form a 60% sparse tensor. And as you probably have noticed that this sparsity is tightly related to the multiplication of the fractions. Each one of them is coming from a specific rank choice. So we can do some other combinations to form a more sparse tensor. And as you can imagine, we can mix and match all of the ratios that's available and have 12 different sparsity degrees supported by this pattern. And this kind of flexibility allows us to present a wide range of sparsities with many degrees, with only a few of them supported at each rank. So in addition to the flexibility, the nature of HSS also enables modularized acceleration in hardware. And we are going to use this example accelerator architecture organization again, where each level in the architecture will be called an architecture level. And naturally, because we have multiple ranks in HSS, we can implement the acceleration next to different levels in the architecture. So for example, next to global buffer, we can implement the acceleration for rank 1. And next to buffer, we can implement the acceleration for rank 0. And using our previous example, the rank 1 will only need to support 4 degrees, and rank 0 only needs to support 3 degrees. So by doing this, the hardware implementation for each rank's acceleration becomes simple and low overhead. And in general, it can lead to much more efficient processing to support the same number of sparsity degrees in hardware. So motivated by these two opportunities, we propose a highlight architecture, which is a flexible and efficient sparse DNN accelerator. And here we're showing a very high-level architectural organization of the design. And what I want you to focus on is the fact that it's a design that supports 2-rank HSS with the rank 1 acceleration next to global buffer and some rank 0 acceleration inside the PE. And specifically, each rank is implementing a skipping SAF, which we call this hierarchical skipping. And this can reduce both the latency and energy consumption, if you recall from our previous section. And we also perform HSS-based compression to reduce the required storage as well as energy consumption as well. So in general, the goal of highlight is to translate 2-rank HSS into reduction in latency and energy. And because of time constraint, I'm not going to the details of this design, but let's take a look at some experimental results related to highlight. First, we compare highlight to some representative designs from different design categories of sparse DNN accelerators. So dense accelerator, structure sparse, 2 structure sparse accelerators, and unstructured sparse accelerator. And specifically, first, let's take a look at some different hardware evaluation metrics for synthetic workloads with different sparsity degrees. On the x-axis, we're showing energy delay squared, energy delay product, cycles, and energy. So these are different hardware metrics. The y-axis is showing the geo mean of these metrics across the synthetic workloads. So lower is better. If we look at the comparison of highlights compared to these existing works, it is always able to achieve the lowest no matter which hardware metric that we're looking at. So in general, the hardware is very efficient given specific sparsity. So what then we want to evaluate is, can we apply the different patterns to the real DNNs and look at accuracy and hardware performance trade-off? So specifically, let's use ResNet 50 as an example. So the y-axis is showing the accuracy loss. And this is because we're pruning the network with different sparsity patterns. The x-axis is showing the normalized energy delay product. So we want both metrics to be as low as possible. So one point to be closer to the lower left corner. And if we look at the design's performance in terms of accuracy loss and hardware efficiency, the highlight design is always sitting on the Pareto frontier. So that means with actual DNN models is always able to produce or provide good trade-off for accuracy and hardware efficiency. Does this answer your question? Okay, nice. And then we also evaluate the same metrics on another different model transformer. This is a attention-based model, and we have much denser activation in our evaluated model. So as a result, a highlight is performing even better compared to the STC, which is the unstructured sparse accelerator, because it pays too much overhead for all of the sparsity-related optimizations. Okay, so with these 2 example workloads, we also evaluate some other ones. But with these 2 example DNNs, we are able to show that highlight sits on the accuracy energy delay product Pareto frontier. So a quick summary of this topic. We first introduced hierarchical structure sparsity, or HSS. which is composed of multiple levels of simple sparsity patterns, and it allows us to have a high flexibility to express a diverse sparsity degrees. And motivated by the nature of HSS, we propose the highlight accelerator, which supports 2-rank HSS for a few degrees at each level. And this allows us to implement low overhead support for each rank at different architecture levels and ensures both efficiency and flexibility. In terms of experimental results, highlight outperforms existing work in terms of various hardware performance metrics, and it sits on the accuracy performance Pareto frontier for representative DNNs. Okay, so that concludes the most important contributions of this work, and I would like to give some high-level key takeaways of this thesis. First of all, we provided a consistent design description based on systematic taxonomy that can help us to facilitate communication between designers from different communities. We then demonstrate that we can perform fast, flexible, and accurate modeling with Sparseloop, which is a early design stage modeling structure. And this can help us to perform evaluation and exploration at early design stage for different sparse tensor accelerators. We also propose a DNN sparsity pattern hardware co-design approach to ensure both flexibility and efficiency, which was critical to next generation accelerator designs.